Hello everyone. Welcome to Controllers Tech. As the title says, today in this video, we will see how to write the basic library for the NRF24L01 transceiver. This is a very long video, and that's why I have split it into 3 parts. The first part will cover the basic setup and configuration. This configuration will remain common for transmit and receive section. In the second part, we will cover the transmitting data. And finally, in the third part, we will see how to receive data. My aim through this video is not to provide you with some library, but make you understand how to write one according to your requirement. Anyway, the link for the code will be in the description, but I would suggest that you write your own code. Let's start with the datasheet then. I have here the datasheet for NRF24L01. It's a transceiver, which works around 2.4 GHz range. I am saying around, because we can set the working channel, and hence the frequency. Let's go through this datasheet, and we will see some important things that we will be using today. We have the pin description here. We have CE pin, which is a digital input. CE stands for chip enable, and it will be used to enable or disable the device. This pin is input to the NRF, not the microcontroller. It will be output from the MCU, and input to the NRF. Then we have chip select pin, we have clock, MOSI, and MISO. And finally the interrupt pin, which we will not be using today. Keep the supply voltage less than 3.6 volts. These are not needed. Here are the operational modes. We will be only focusing on our X and TX modes. We will use these configurations later, when we will set up the registers. It supports the air data rate of 1 megabits per second, or 2 Mbps. Then we have the RF channel frequency. It have the base frequency of 2400 MHz, and later we can add the channel number, to change this frequency. Each channel will increment the frequency by 1 MHz, if you are using the data rate of 1 Mbps, or by 2 MHz in case of 2 Mbps data rate. We can also set the output power according to our requirement. We will not be using enhanced shock burst for this tutorial. We have to set the payload length during the configuration, and it can vary between 0 to 32 bits. It supports auto acknowledgement. It is basically when the receiver sends the acknowledgement to the transmitter, but we will not be using this today. Here we have the addressing system for the data pipes. Pipe 0 have unique 5 bytes address, and between pipe 1 to pipe 5, the 4 most significant bytes are shared for the address. Only the least significant byte changes for these pipes, and keep in mind that the address register for pipe 2 to pipe 5 is only 1 byte wide. We will see this in the receiving part of this video. Then we have here is the SPI related information. We can use the maximum data rate of 8 megabits per second. We will write the MSB first using the master. Now we have reached the main part of the datasheet. So here we have our certain commands, which are like some special commands. These commands have some specific functions. For example, if we want to send the payload, we must use this command first. This will inform the NRF that the next data is payload. Similarly, before receiving the payload, we need to send this command. And this one here is to flush the RX FIFO. You will understand them once we will start writing these registers and payloads. Now finally we have arrived to the registers. Before I continue any further, let's create a new project in the Cube IDE. This is basically the setup part for STM32, and if you are using any other microcontroller, you can set up the SPI, and that's all. I am using STM32F407ZE controller. This is the controller I am using. The reason for the use of this is, because it have the connector for the NRF on board. You can see this connector, and here I have attached the transceiver, as simple as that. Let's give the name to this project, and click Finish. This here is the Cube MX, let's do our regular setup now. I am selecting external crystal for the clock. I have 8 MHz crystal, and I am running the CPU at maximum 168 MHz. Now we need to set up the SPI. If you take a look at the schematics, you can see the NRF is connected to SPI1. We will use the full duplex mode. Note here that 3 pins got selected for the SPI1, and they are PA5, A6, and A7. We need to keep the SPI clock below 8 megabits per second. Let's see the schematics again. SPI1 pins are actually the pins PB3, PB4, and PB5. So I will remap the SPI to those pins. Also NRF-CE is PG6, and CS is PG7. So let's select them as the output pins. I also want to select the LEDs for the status purpose. They are pins PF9 and PF10. That's all for the setup. Click Save to generate the project. Let's create a new source file, where we can write the NRF related code. In order to communicate with NRF, we need to write and read the data from the registers. To do that, we will create a function to simplify this operation. This function will write data to the particular register, and its parameters will be the register, where you want to write the data into, and the data itself. Before that, let's define the chip select pin, and the chip enable pin. Now create a buffer, which can hold 2 bytes of data. The 0th byte is the register, and we have to write a 1 in the 5th position. This is because it's given in the datasheet that, whenever we have to send the register address, the 5th bit must be a 1. These 5 A's are the 5 bits of register address. Now before we start writing to the slave device, we must pull the CS pin low. I forgot to change this to CS. I think it's better if we create a separate function for these pins. This is for selecting the slave device. This is for unselecting the slave device. CE enable will enable the device, and CE disable will disable the device. Now we will simply call the chip select function. Next we will use HOL SPI transmit, to transmit the data to the SPI. We need to define the SPI handler first. Let's call it NRF24SPI. Here we will send the buff, the size will be 2. The first byte will be the data byte, and let's give some timeout. Now we will release the device, by pulling the CS pin high. Sometimes we need to write multiple bytes in sequence, and that's why we will create a separate function for it. It will basically be the same code, except first we will send the register address. And then we will send all the data bytes at once. These functions are used in similar manner in other devices also. Take any SPI device, you will need these functions in order to communicate with it. Now let's write a function to read the data from a particular register. This function will return the data. Again we will use the same code. But if you see the datasheet, we don't need any special instruction for the read. We just have to send the 5-bit register address. So here we will simply send the register address, where we want to read the data from. Let's define a variable, where we can store the data. And now call whole SPI read, to read 1 byte of data from the register. And in the end, we will return this data. This is the function to read multiple data bytes, starting from this register. Pointer to the variable, where you want to store the data, and the number of bytes you want to read. Let's write a separate function for sending those special commands. These are the ones I am talking about. These commands are standalone commands, and they don't need to be written to some register. So we are creating a new function, specially for them. The procedure will be same: select the device, send the command, and release the device. This completes our general SPI functions for any device. Like I mentioned, these functions can be, and required to be, used in any SPI device. Let's write a function to initialize the NRF24. Here we will start configuring these registers, starting with the first one, config register. Before we configure the registers, we need to disable the device, and after configuring, we will enable it. Let me change these to enable, and disable. We will disable the device. Actually, we don't need to call this chip unselect here, I am just calling it. Let's see the config register now. To put the device in receive, or transmit mode, we will write a separate function for that. Also, we will power up the device, after putting it in the RX, or TX mode. So these 2 bits will be configured later. We are not using any CRC today. Then we have some interrupt-related bits, which we won't be looking at today. So the config register will be 0. We will use NRF write register, to write the data to this register. But before that, let's create a new header file, and let's call it NRF24L01.h. Here I am defining addresses for all the registers, and also the commands. This will make it easy for us to write the values to the respective register. Let's include that file here. I think I need to build this once. Okay, now it shows up. So the config register will be 0. Next register is to enable the auto acknowledgement. This will enable the auto acknowledgement by the receiver, after successful reception, but we are not using it today, so we will write 0 to this register also. So let's write 0 to disable auto acknowledgement. The next register is to enable the data pipe for reception. To enable any data pipe for receiving data, you need to write a 1 in that position. Again, we will do this setup when we will be setting the receiver mode. For now, we are trying to do the general setup, which can be used in both the transmitter and the receiver mode. For now, we will disable all the pipes. Next register is to set up the address width. Here we have to set how many bytes the TX and RX address are going to be. Only the first 2 bits of this register can be modified. We will use the 5 bytes for the address, and to do that we will write 0x03 to this register. Next is the setup for automatic retransmission. When the transmitter does not receive the auto acknowledgement from the receiver, the transmitter can retransmit the data. Here we can control how many retransmissions can be done, and at what interval they will be. But since we are not using auto acknowledgement, we will disable this entire register. So write 0 to this register. Next is the channel selection for the transmission. We just have to put the channel number in this register. For now, we will write 0 here, and later, when we set up the TX or RX mode, then we will set up the channel also. Next register is the RF setup. Here we can set the data rate, and the transmission power. I am setting everything to the maximum, so data rate of 2 Mbps, and power of 0 decibels. Take care here, the 0th bit is not being modified, we are modifying bits 1 to 3. We need to write 1110, that is 0x0E. So write 0x0E to the RF setup register. Status register can be used to check the status of data received or transmitted. Observe TX is also read-only register. Here we can write the address for the data pipes. We will set them up during the mode setup. Here you can set the length of data in the data pipes. Again, we will set up later. FIFO status can be used to check the status of RX FIFO and TX FIFO. And we are not using dynamic payloads, so no need to check other registers. This is it then, this completes the initialization of NRF24L01. This configuration will remain common for both the TX mode and the RX mode. That's why we are using a separate function here. This is it for the first part of the tutorial. Next part will cover the transmit mode and the data transmission. The link is in the description. That's it for this video. Keep watching, and have a nice day ahead.